In the first section of the video, we have talked about upper bound and lower bound. And in the second section of the video, we are going to talk about maximum and minimum of a set. So let's first define what minimum and maximum of a set means. So let L be a real number, and we call this real number a maximum of S if, first of all, L lies inside the set. Second, we require L to be an upper bound, which means L is greater than or equal to X for all X inside S. So similarly, we can define what minimum of S mean. Minimum of S means, first, we still need this number to be lying inside the set. Second, we need the number to be smaller than or equal to X for all X inside S, which means it is a lower bound. So there are several remarks concerning maximum and minimum. First of all, similar to upper bound and lower bound, it may or may not exist. Why? Because for upper bound and lower bound, we know that it may or may not exist, and we require maximum to be upper bound. So if there is no upper bound, then there is no maximum as well. The second remark is that if maximum and minimum exist, then it is unique. Here, unique means that there is only one maximum or minimum if it exists. So I'm going to prove the second statement. So let's suppose L and L prime are two maximums. So to prove that they are the maximum is unique, it is similar to saying that to L is equal to L prime. So how can we prove it? So first of all, by the definition of maximum, L should be greater than or equal to X for all X inside S, and L prime should be greater than or equal to X for all X inside S. And also, L and L prime should be lying inside the S. This is just the definition. So if L prime is inside S, then we can replace this X by L prime. So we obtain the first inequality Y at L greater than or equal to L prime. Similarly, we have L lying inside S, and by the second statement, L is lying inside S, so we can replace this X by L, and so we have L prime greater than or equal to L. So collecting these two informations, L is greater than or equal to L prime and L prime is greater than or equal to L, that implies that L is equal to L prime. So I'm not going to do the dirty work again for the minimum, and I can tell you that indeed the result of maximum can be extended to minimum. And how can we do so? So first of all, we have to see a lemma first. So the lemma says that if we define negative S as this set, well, what is this set? This set is simply taking a minus sign to the elements of S. If epsilon is minimum of S, then negative epsilon is a maximum of S. How can we prove it? Well, first of all, if epsilon is the minimum of S, then that means epsilon is more than or equal to X for all X inside S. So to prove the statement, we need to prove that for any Y inside negative S, Y can be bounded above by negative s, negative epsilon. So how can we do so? First of all, by the definition of negative s, we know that there exists some x inside s such that negative x is equal to y. Well, this is just the definition of negative s. And we take the negative sign to both sides, and we will get x equal to negative y. Now, as x is an element of s, by the first statement we have said we have epsilon is smaller than or equal to x, and x in this case is negative y. So if we take the negative side to both sides of the inequality, we get negative epsilon is greater than or equal to y. Also, epsilon is lying inside s, and that means negative epsilon lies inside negative s by the definition of negative s. So, indeed, after checking these two conditions, we know that negative epsilon is a maximum of negative s. So, using this lemma, we can finish our proof. So, let us assume P and P prime be two minimums of S. Then negative P and negative P prime are two maxima of negative S by our lemma. So by our previous argument, these two maximums should be the same. So negative P is equal to negative P prime, and if we take negative sign to both sides, we get P equal to P prime, and that means the two minimums are indeed the same. And we have proved that the minimum and maximum are unique. So after proving this, let's do an exercise. Well, we encounter this set again, and we say that it has no minimum and maximum. Well, the first statement, maximum, it has no maximum. I will leave it as exercise. And for the part of minimum, we suppose that is indeed a minimum, and we call it mu. So first of all, mu should be lying inside S by the definition of minimum, and by the definition of this interval, we know that mu is greater than 0. And if we divide both sides by 2, we still get mu over 2 is greater than 0. And by the definition of this interval, mu over 2 again lie inside this interval. And on the other hand, by the definition of minimum, mu is smaller than or equal to x for all x inside this interval. And as mu over 2 is inside this set, we can replace this x by mu over 2, and therefore we get mu is smaller than or equal to mu over 2. So multiply both sides by 2, we get 2 mu is smaller than or equal to mu, and if we subtract mu by both sides, we get mu is smaller than or equal to 0. Remember, we have proved that mu is greater than 0, but now we found that mu is smaller than or equal to 0. These two statements indeed are contradictory. And so, if there's a contradiction, that means there should be an error where we do an assumption. Remember what our assumption is? Our assumption says that there there is indeed a minimum for this interval. And as we found a contradiction, that means this assumption is indeed wrong. And what is the negation of this statement? The negation is that there's no minimum, right? Okay, so we have proved that this interval indeed do not have any minimum or maximum, and that's all. So this is the end of our section about upper bound, lower bound, minimum, maximum of a subset of R. And see you in the next video.